as you can see right here in this northern zone, there was a magnitude 7.6 in 2005. I was 9 years old at the time, and I was one of the people who was a part of that earthquake. Like, I was there, I lived there. And that also prompted me to want to be a geologist someday.
Good morning and welcome to our Geology Hour, sponsored by the Geological Society of Oregon Country. My name is Carrie Gordon. I am a retired geologist here in Central Oregon. The next two folks I'm going to introduce are Angela and Javaria. So, because we'll get Angela on first, Javaria, would you like to introduce yourself?
Yes, absolutely. Thanks for having me. I'm Javaria, and I'm a second-year master's student at Portland State University, and I'm doing my master's in the Central High Cascades of Oregon, so it's very exciting, and I'm sure that I'll talk about it more eventually at some point.
And Angela, would you like to introduce yourself and then take it away for the Geology News Part 1?
Okay, thank you. Hi, everyone. So I'm Angela. I'm also a second-year grad student at Portland State University. Javaria and I actually have the same advisor, Dr. Martin Strack. So my research is actually kind of like on the Columbia River basalts, but not, because we don't know yet what these basalts are from. So I'm focused more in Eastern Oregon over towards Monument Dike. So Heather and I have a lot of similarities in our research as well. So I'm excited to see Heather. So before we get to Heather and Javaria, I have my story for you. So I'm going to go ahead and share my screen. Okay, so this story is kind of out of this world, which I think is great because Halloween is just right around the corner, so it seems almost fitting. Many of you have known about the earthquake that happened on September 8th in Morocco. It was a 6.8 magnitude earthquake, but a lot of people haven't heard about these strange lights that were reported beforehand. I was made aware of them by this article that my sister shared with me from CNN. That's this year. That actually reported on many people seeing these lights. Although this picture here is not of Morocco, apparently it's of Mexico City. So anyway, basically they call them earthquake lights. And what they are is a luminous phenomenon that are associated with earthquakes. And they find that they're usually around a 5.0 magnitude or greater. They often occur seconds to weeks prior to an earthquake, or during an earthquake, or immediately following an earthquake. And they can be seen up to 600 kilometers away from the epicenter, but that is proportional to the magnitude. So the bigger the magnitude of the earthquake, the farther away you're going to see it. Like the 600 kilometers, I think it was an 8.2 or something. They also have been found to mostly occur along deeply penetrating subvertical faults, usually normal and strike slip faults. But there has been like one or two accounts of them occurring at a subduction zone. They are suggested to occur due to a rapid buildup in stress prior to rupture. And this could actually be very important to us because being that it happens prior to an eruption, we can actually forecast these earthquakes and get people to safety, hopefully saving a lot more lives. So it is suggested that these occur due to naturally occurring charge carriers that propagate through the surface where ionization produces light. And so that process basically is these charge carriers are naturally formed within our rocks, usually like a igneous or metamorphic rock. And then during stress, they are dislocated and they can move. So these charge carriers are basically p-holes or positive ion peroxy links or positive hole peroxy links. And these peroxy links, if you can see, your screen is not in the middle of it, you can see these two O negative ions are bonded together and they're very weak. And so when stress comes and dislocates them, it creates this positive hole. And those positive holes propagate through the surface equally around. And as they get to the surface, they kind of accumulate. And then that accumulation will build up an electric charge, a magnetic field, or an electromagnetic emission. Electromagnetic emission. And then so when that occurs, they build up into they diffuse into the atmosphere, and they create an ionized air, and which creates these lights. Okay, so being that we have a lot of normal faults and strike slip faults, and we even have a strike slip fault right off of or not strike slip, subduction right off our coast, that would be a great idea for me to share the different types of earthquake lights that have been reported, so that in the event that we might have a 5.0 greater earthquake, we might be able to recognize. So first we have the earthquake lightning, which is like the distant lightning that you see in the sky. It lights the sky, but you can't hear the thunder. And then we've got the horizontal or vertical bands in the atmosphere that look a lot like the aurora borealis. Then there's the orbs. And this is why I say this is out of this world, because a lot of people have reported orbs as being associated with Sasquatch or with UFOs and aliens, or something that nobody can really explain. They're just these lights in the sky, little round balls in the sky or in the air. And then fire tongues, which are like ignis fatuus, which I have never heard of, but apparently it flickers or moves along the ground surface. And so I couldn't find any pictures of that it was associated with earthquakes. But in the article that has this photo, it actually talked about how these orbs floated up around the surface and met up with these two little orbs up here. So I thought that would be a good example. And then we've got seismic flames that emerge from the ground, but they don't leave burn marks on the ground afterwards. And this is an old black and white picture from the 70s, so it's hard to tell. But these little white things in the black background are basically the flames. And then there's the coronal and point discharge lights, which kind of look like the halos that are around the sun, or around the moon, or they can be like a searchlight type light that just streams across the sky. And then finally, there's the luminous clouds. They're rare, but I was able to get some screen capture from a video in China. And basically, there's clouds that are lit up like rainbows. And so that is about it. If anybody has any questions.
Oh my gosh, we just had Dr. Scott Fisher from U of O talk about exoplanets and talked about a little bit about the new term, which I'm spacing on, for UFOs. Oh my gosh, this adds a whole new flavor to lights in the sky, Angela. This is amazing.
I agree. It's exciting. Now it'll be, is it a UFO? Is it Sasquatch? Or is an earthquake coming? I don't know.
Does anybody have any burning questions about lights in the sky?
Yeah, this is Carol. So that's fascinating, Angela. I've never heard of this before, and I love your pictures. This last one with the luminous clouds, I'm thinking that energy must be attracted to the clouds to go off there.
Yeah, so basically the way there wasn't a lot of explanation on these, because apparently they don't happen as often as everything else, but just like the charge carriers can get stuck, accumulate at the surface, they can also accumulate at that boundary in the atmosphere between the two different spheres. And then that creates, at the cloud level, it creates those lights.
Thank you, Angela, for explaining those lights in the skies.
Yes, thank you.
Joe actually says it's interesting that earthquakes can happen these lights can happen weeks prior if they're caused by the dislocation of an earthquake itself. That's kind of an interesting relationship, like a precursor type of thing.
Yeah, that's the one thing that kind of confuses me about it. I mean, can we really attribute it to an earthquake? Because it's not like
Whoops,
it takes a long time for a rock to break, but at the same time, there is that stress buildup within the mineral grain before it breaks. So, I mean, it's possible and it's not possible. I'm not sure.
All right. Thank you. Javaria, what have you got for us?
Hi, so yeah, I'm gonna carry the same earthquake theme because I think it's the theme of the day is earthquakes, which I feel like is the theme of this month, really. So I'm gonna be talking, let me share my screen. So I'm gonna talk about the earthquakes in Afghanistan. And there's been a series of earthquakes that we've seen in the news, but it really has kind of fizzled away from the mainstream news. And I didn't really see a lot of reporting on it. So I kind of want to talk about it because these were really major events. And then I want to talk about the seismic potential in that region, and I'll tell you why in a little bit. And also, I want to talk about the earthquake safety aspects in that part of the world, because I don't think that we get to know too much about the seismic hazards in especially that part of the world. And so, first of all, there were a series of earthquakes in that region, and the biggest one that started it all off was the 6.3, and then after that 6.3 there was a 5.5, a 4.7, a 6.3 again, so another big one, and then 5.9, 4.6, 4.8, 4.9, so a lot of earthquakes that were all about 40 kilometers, which is like 25 miles away from the northwest Herat city area, which is right here on the western edge of Afghanistan. And so the first one happened, which was the 6.3, that happened on October 7th, which was a Saturday in the morning. And then a series of aftershocks that I just mentioned happened right after. And then there was another big one, which was another 6.3, which happened on October 11th. That was a Wednesday, the following Wednesday. And that was about in the same region as well. And so this caused a lot of destruction in Afghanistan, and it killed more than 2,000 people. So it was a significant event. And just to understand where this is happening, so here's this tectonic map of Afghanistan. And right here, you can see that this is that boundary area where the Indian plate is having this continental collision with the Eurasian plate right about here. And so that's where you have this transpressional plate boundary where this Chuman fault zone lands. And then there is this other area of all this accreted terrain, and then this platform, that's the North Afghan platform. And there are these three major large fault structures that are the big seismic hazards in this area. And so this Herat fault is where the earthquakes that just occurred happen. And this next map is a seismotectonic map of Afghanistan. And we can see that this is data that's been collected of earthquakes from 2000 BC all the way up to 2007. And so these red are all the magnitude earthquakes that are greater than magnitude 7. So this area is capable of producing really large earthquakes. And I put in this box right here the fault zone where this current earthquakes had occurred, which is right about in this region. And there's the Herat city right here. And so we can see all these mini faults associated. And I love this map because it shows the terrain that's underlying as well. And we can see all that compressional regime forming this very amazing terrain in this area. Here's another map of the earthquake distribution. And this not only just shows Afghanistan, but other countries right around it. And we can see Iran has a huge amount of earthquakes that occur, and these are all earthquakes in the more recent years, and all the red dots are these earthquakes that are at a depth of less than 35 kilometers. So these are all predominantly shallow earthquakes. And these are all these earthquakes in this northern section where we saw that plate boundary with the most amount of compressional stresses. And then one of the very reasons that I got very intrigued by this event and wanted to talk about it today is that this country right here, Pakistan, that is east of Afghanistan, is where I'm from. And I was born in Pakistan.
And so I wanted to talk about it. And here's a map of Pakistan and the seismic zones associated with Pakistan. And as you can see on this map, there are 5 major seismic zones in Pakistan, and all of them in the last 100 years has produced earthquakes greater than magnitude 7, just in the last 100 years. And the map shows the date and the magnitude of the largest earthquake that each zone has produced. And as you can see right here in this northern zone, there was a magnitude 7.6 in 2005. I was 9 years old at the time, and I was one of the people who was a part of that earthquake. Like, I was there, I lived there. And that also prompted me to want to be a geologist someday. And so that's like my fun geology story, but that was a major earthquake. And the shake time for that earthquake was a whole minute. It was 60 seconds. And this basin was completely overwhelmed by the shaking. And I reported the number of deaths and injuries and people displaced in that event. And it was a very significant event that killed more than 87,000 people. Luckily, myself and my family didn't die. So another thing that I wanted to talk about was earthquake safety in that area, because it's very different from this part of the world. Something that I don't think that we really realize if we've lived here all our lives, but the building codes there are not up to earthquake standards. And it's too much to ask for from countries in that part of the world to completely re-up their building codes because they don't have the funds to do it. And so the buildings are still those old concrete buildings that are not retrofitted and that are not up to that standard of surviving through earthquakes. And so with those building structures, the rule is not the drop, cover, and hold, which is the rule that we follow here, but instead the safest place to be in an earthquake is under door frames and staircases. And so this is a photo from the earthquake in Afghanistan, the current one. And you can see that this entire structure has collapsed, but the door is still standing. And the door is always, I was told, and that's what my family did during the big earthquake that we survived, was that stand under a door, stand under the staircase, because those are the safest places to be. But that's not what we do here. I have more pictures of the destruction from this Afghanistan earthquake. I tried to find the pictures that didn't have people in it because I don't want to impose that stress on everybody on a Saturday morning. And so this is just to show the destruction of all the stuff that's broken down. And that leads me into my next very important thing that I really think that's why it's so important to have events like the Great Shakeout and other events talking about safety and earthquake safety here, because for people that have lived here all their lives, you know, you're doing this drill since kindergarten and probably it's reinforced in our brains of what to do. But we have a lot of international students, people from places that have never experienced earthquakes, or people from places that have experienced earthquakes, but their safety standards are very different because, like I said, I was always told to stand under staircases, but you're not supposed to do that here in the US. So that's why it's very important to integrate this. And I know in the academic community, in schools, we have the Great Shakeout and everything, but I think that in other communities as well, it's really important to talk about it because, you know, we're a melting pot society, and it's important that everyone can stay safe in these events. So that was my little spiel. And is there any questions for me? I'm going to stop sharing.
Actually, we do have one. Carol, would you like to ask your question?
Yeah, you talked about the fault zone as being transgressional. Can you do, is that like a subduction zone with some lateral component as well? Can you talk about the type of fault it is a little better?
Yeah, so it's basically this compressional fault regime where it is not a subduction zone because it's a continental and continental collision. So what we have here is that there is this chunk of land, which is the Eurasian chunk of land and then the Indian chunk of land. And now that these lands are coming together, they're both continental crusts, and neither of them can subduct underneath each other because they're both the same density. So then they're having this compressional regime, which is why there's this huge belt of mountains in that area, which is why the Himalaya mountains are there, the Hindu Kush mountains are there. And so this is this entire compressional regime, which is creating all these mountains, but also imposing such a high amount of stress and structural deformation.
Oh, thank you. And I just want to make a comment that I was a structural engineer, and I went to an earthquake engineering research institute meeting once, and they were talking about different kinds of base isolation they were designing for areas that had a lot of unreinforced masonry buildings and stuff. And I think the problem is getting the information out to everybody to build in a way that, using their available materials, that they can build safer buildings. So that's just a comment on that. It's not like there's no research being done on that, but it's really hard to disseminate information.
Absolutely. And just getting that information out to the public, and also being able to, have the funds to be able to do that. And I know that Pakistan and that part of the world in general, Afghanistan, all those countries don't really have the resources and the money to be able to do that. And they're very densely populated areas. And that's why so many people die. Like Pakistan's population is 231 million people. So
they were trying to address some of those problems, like using old tires and things, just stuff that's laying around.
Mm-hmm.
And to have survived that earthquake, oh my gosh, Javaria, I can remember one in the 60s in Ellensburg, Washington, where we heard jars rattling on the shelves, and it was a major earthquake in Seattle, but nothing like what you've survived.
It was scary.
I'm glad you got into geology.
I know. I'm so happy. That's my geology story.
That's wonderful. We do have another question that came in from Leslie. Do you have any information on the recent Mount St. Helens small earthquake swarm? Have either you or Angela run into that?
I personally haven't really looked too much into that. Maybe Angela might have something for us.
I check earthquakes on Mount Hood daily, at least once a day. And so I do know that Mount St. Helens is known for these earthquake swarms that happen usually 10 during a month, 10 earthquakes in a cluster in a month's time. And they can have as many as 10 earthquakes per week, but a lot of times they'll cluster themselves and just, do these little swarms. And Mount Hood does the same thing, but not as frequently as Mount Hood. So I think that might be an interesting topic for me to focus on in a later month, in a later meeting, because I think a lot of understanding of how to recognize earthquakes that are associated with volcanism, that's what I want to do for my doctorate. So I think that would actually be something really cool to talk about.
Well, I don't know about the rest of you folks viewing today, but I am just totally impressed with what both of you brought to the table today. Thank you so much.
For Javaria, for your research in geology, you talked about the compressional features of the mountains. Basil Tikoff has just had a GSA Penrose conference and has a paper called Hit and Run, which talks about how the terrains hit in Riggins, Idaho area and cause that same compressional features, and you can actually go there and see the rocks. She might be interested in knowing more about that. You can read his papers.
Yeah, that would be incredibly useful.
Oh, that's wonderful. So, launching into our talk today, oh my gosh, we're going to learn about the geochronology and geochemistry of the monument Dike swarm. And Heather, I apologize, I don't have your background history to read. So would you mind starting out by introducing yourself and how you came to be on this particular topic, and then take it away.
Yeah, so hi, I'm Heather Ziff. I'm an undergrad sociology, geology double major at Portland State University. I have the same thesis advisor as Javaria and Angela. I'm actually doing work that's expanding on a master's thesis. So I'm taking a small piece of it and kind of looking into that a little bit more deeply. So, as I said, I'm gonna start bigger picture and then bring it back a bit. So this project was conducted as a small piece of a larger project intended to locate crustal storage sites for the Columbia River basalt group. This is one of many volcanic features created as a result of the Yellowstone hotspot, which we now know is currently located beneath Yellowstone National Park in the Montana, Idaho, Wyoming area. There are a couple of key processes I wanted to dive into a bit because they're really quite crucial for the formation of this flood basalt province. First of all, we're located on a subduction zone where the Farallon plate is subducting beneath the North American plate. I apologize, this might seem a bit disjointed at first, but I promise it'll all come together. The second big process we have going on here is this hotspot, right? So hotspots originate at the core mantle boundary. They rise through the mantle, creating a plume head with this large region of really high temperatures and the plume tail that follows. Melting of the material above the plume head results in flood basalts or large igneous provinces like the Columbia River flood basalts. And melting above the plume tail creates this hotspot track. These features trace their way across the lithosphere as it floats and moves above the mantle and the largely stagnant mantle plume. So just to get an idea of flood basalts around the world and kind of the significance here, we see the Columbia River flood basalts pictured with respect to other flood basalts around the world. One of the things that's most interesting to me about flood basalts as a whole is that they're big drivers of climate change and they're responsible for the largest mass extinctions on Earth. So like the Deccan traps in India, for example, are responsible for the Cretaceous Paleogene or the KT boundary, like that mass extinction, and the Siberian traps were responsible for the Permian Triassic extinction, which was the largest in history. So the Columbia River flood basalts are the youngest flood basalt on Earth and therefore have some of the best preserved features, which is a fantastic opportunity for studying these events. Looking at a diagram, or like this diagram on the right now, we can see that the volumetric output of these large igneous provinces are in general. Continental flood basalts are pictured with the diamonds, and then oceanic LIPs, or those oceanic plateaus, are pictured with the blue squares. And one of the big things we notice is that the CRBs are really small compared to other flood basalts around the world. And why that is has led to a lot of questions about trying to explain the processes that might have resulted in the deposits we're seeing today. So here are a couple of really complicated maps and diagrams that I'm not going to go into full detail about, but there are a couple of large scale patterns I wanted to articulate. So the first idea is this like little figure on the left. The blue blob represents the oldest evidence of potential lithospheric hotspot impingement. So in this scenario, we have this area called Silesia, which was created as a result of the plume head impinging through oceanic crust and then later accreted onto the western margin of North America. And what's extra enticing about this is that when the volumetric output of Silesia is included in diagrams like the one in the previous slide, it actually does plot within the range of global flood basalts. But while this is enticing, this piece of evidence alone does not paint a very clear picture. If Silesia is in fact the superficial representation of the mantle plume head, why is there a separate continental flood basalt province just inland and not just an expression of the plume tail? So that's kind of what this diagram on the right here is getting at. We can see a few things happening. Of note is the reaccumulation of a plume head below the subducting Farallon plate. And the basic idea here is that over time, as the North American plate moved over the hot spot, the Farallon plate acted as a shield, preventing the hot spot from extruding. Over time, heat accumulated. There are a bunch of theories that are still really widely debated that try to explain the mechanics by which the Farallon plate eventually broke apart. But regardless of the mechanism, this pseudo plume head was able to escape and baked the base of the continental lithosphere. Magma extruded through these like fissure dikes, which are these vertical features, and sills, which are these more horizontal features. And superficially, we see this expressed as the Columbia River flood basalt province. So here I just wanted to provide like an idea of what we're looking for out in the field. These pictures are both fissure dikes. On the left, this is Iceland, present day. They express themselves as relatively linear features in the landscape, and they extrude basalt, which is very silica poor, not very viscous, so it flows out in sheets. And then on the right is actually a picture of one of the dikes in the Monument Dike swarm. There's kind of these like fin-like features with relatively horizontal columns that cool perpendicular to the cooling surface. Yeah. So now we're actually getting into more my study area. So the Columbia River basalt group is divided into several main flow units, erupted from several regions with a high density of dikes that we call the dike swarms. Magmatic activity began in the south with the Steens and Monument Dike swarms, erupting the Steens and Picture Gorge lavas respectively. My field area is outlined with a little rectangle. And then later on, the Chief Josic Dike swarm sourced the Grand Ronde and Imnaha lavas. And the Chief Josic Dike swarm actually erupted about 85% of the material of the flood basalt province. So Picture Gorge is relatively minor volumetrically when compared to the rest of the CRVs. So the purpose of this slide is really to show our understanding of how Picture Gorge basalts have changed through time. You can kind of ignore this magnetic polarity section as it's not quite as relevant for this project, but it's important to notice the difference between the distribution of Picture Gorge basalts in 2008 versus 2020. Picture Gorge basalts weren't established as a main phase unit of the Columbia River basalt group until the 80s. And they weren't treated with modern age dating techniques until Emily Cahoon's study in 2020. This study is particularly interesting and important because it highlights that Picture Gorge wasn't only a minor eruptive unit contemporaneous with the Grand Ronde basalt, like was previously believed, but actually erupted earlier and longer than any other Columbia River basalt main phase unit. This highlights Picture Gorge as an important understudied unit for understanding how these magmas have evolved through time. So now focusing on the goals of this project, as I mentioned earlier, samples were collected by PhD candidate Rachel Sweeten in 2021 as part of her master's thesis. She performed XRF and ICP-MS trace element geochemical analyses on various samples for her project and used machine learning trained on 4 previous data sets to identify each sample with its respective flow subunit. These samples and the findings from her analyses built the foundation for this project to be possible. And from that, my project goals were to use these flow member designations to infer eruptive histories of the selected samples, age date the dikes using argon-argon age dating techniques, and constrain this like intrusive activity or activity of the plumbing system, and compare my dike ages to the flow ages found by Emily Cahoon to better understand the chronology or like order of eruptive activity. Yeah, it's just a deep dive on the ages. So we selected samples for age dating based on magnesium content along a roughly northwest to southeast transect. This was done in an attempt to better understand the age range for the most primitive to the most evolved samples. Primitive samples are typically lower in silica, higher in mafic material like magnesium, manganese, iron, and closer in composition to the mantle or primitive mantle. So evolved samples would be the opposite. So high silica, low mafic materials. Normally we would expect the more primitive material to be older, but and when it's not, it might give us clues to the dynamics of the system over time. Here I have just a few examples of what the features look like in the field. The dikes are most easily recognized as these like distinct fins that jet out above the surface. As the study is located in the John Day area in kind of the south end of the Blue Mountains province, they either intrude through like these like John Day ashes or through terrain rocks like sandstones, serpentinites, chert argillite, etc. They can also intrude through their own lavas, but they're more easily exposed in this easy to erode material because the basalt's more dense comparatively. Yeah. We intended to target ground mass phase for analysis because this accurately reflects the crystallization age of the whole system rather than like a potentially older age like you could get from phenocrysts. So in order to make sure all the samples were good candidates for this, we inspected thin sections under petrographic microscopes to observe their textures. So aphanitic or fine-grained textures are ideal for ground mass analysis because they have a lot of ground mass and they contain very little crystalline material. So most of our samples look like these on the right, where we have these like really tiny grains. It's just good for age dating. And so one of our samples, we had these larger lathes of plagioclase with this phaneritic or coarse grain texture. Because there isn't much of a ground mass, we used plagioclase phase analysis, which may present a slightly older age, might be kind of younger. There's a little bit more, it's a bit more iffy. Like you can't really say it's a definitive crystallization age for plagioclase because it takes longer to cool. So in order to prepare the samples for age dating, weathering grinds were removed with a tile saw. Unweathered sample was passed through the jaw crusher. The crushed samples were sieved so we could attain the 97 to 250 micrometer grain sizes. We washed them in ultrasonic baths to remove clay material. We dried them and separated them out with these magnetic separators, like various different, this is separate like mafic materials, oxides out from like your feldspars and ground mass material. So lastly, we acid leached our material through hydrochloric and nitric acid, various molarities. And then for our one plagioclase sample, we used hydrofluoric acid. And this is just an attempt to like remove the clays or any potential weathering material that might impact the age dates. All right, the last stages before analysis were handpicking grains used for analysis, again, to just try to exclude as much mafic material as we could, because this can cause like errors in our analysis. We packed the samples in these vacuum sealed quartz vials and irradiated them, which is basically bombarding them very rapidly with neutrons. And then lastly, the gases were analyzed using a multi-collector here on the right, which fires lasers really rapidly at the samples to release the argon gas. And then the mass spectrometer separates them out by density, and we're able to figure out how much of each we have, which tells us their ages. So before I get into the list of age results, I wanted to give you an idea of what the age spectra look like and just some of the patterns we look for. On the left, I'm trying to show two different common patterns of age spectra. On the top is on both sides, I'm trying to show these patterns. On the top, we're going to see the plateau graph, and on the bottom, we have the inverse isochron graph. I won't get into the math behind it all too much, but what's important to see here is that for an age to be considered good, the plateau and inverse isochron values must be within error of one another, which was the case for all except for two samples by like 0.01, but there are other values that you'll see later were still in agreement, so all ages were accepted as good or statistically significant. we can see concave down spectra like those on the left. These are generally regarded as minimum ages because of their patterns. And on the right, this is more of like a typical age spectra, not a minimum or maximum. This is just good age. And then the recoil at high temperature heating steps. This often happens from glassy material, which is unlikely given how much we leach them with acid, or it could result from like fibers from tech wipes as we're moving the material around. Either way, we're still able to obtain a plateau through points that intersect with the isochron values. So we're still able to pull data out of it even with the recoil. And here are the ages. Results range between 17.27 and 15.61 MA. The MSWD values are a measure of how well the line fits the data. So the closer to 1 the value is, regardless of if it's above or below, the better the data is fit. All samples are considered to have statistically significant MSWD values, with the exception of RS21 M11A down here. But we were still able to calculate a total fusion age, which is that plateau age. And it holds less statistical weight because we can't calculate an MSWD value, but our analytical error was still quite low. So according to various papers, I'm still considering that one a good age. And it also falls within the range of the expected value for that sample. Now that we've touched on the ages, I'm just going to go through the geochemistry real quick. I plotted the samples on a total alkali Scylla diagram to understand their compositions. When compared with the stratigraphy, flow subunits overlap heavily with one another. Monument and Twickenham subunits are geochemically most similar to one another and plot largely in the basaltic field. Dayville contains nearly the entire compositional range of picture gorge basalt chemistry, and like the samples range from the most primitive to the most evolved. The high magnesium samples in the lower left-hand corner aren't a formal subunit of picture gorge, but they've been regarded by previous studies as a separate category. They've been characterized as especially primitive samples, independent of the flow subunits that may instead represent the composition of the parent magma for picture gorge. But limited research has looked into this, so results are interpreted with a grain of salt for the high magnesium. The point of this graph is to really just highlight the scatter between the flow subunits, with similar trends that to what we just saw with the TAS diagram. So regardless of which graph or analysis is used with these samples, there are little geochemical differences between the flow subunits. This holds true for spider diagrams, looking at compatible versus incompatible elements, scatter plots like these, and it's actually an issue that causes high errors when classifying samples and their respective flow subunits. This isn't a new problem, and it's been suggested by studies since the 80s. This is an idea I'll touch on again a bit at the end. It's just important to keep this idea in mind of the geochemical overlap when interpreting the results. All right, so finally we get to combine the age data with the geochemical data a bit. On the right, we can see the Dike data from this study compared to the flow data from Emily Cahoon's study. The ages obtained for our samples are well within the expected range when compared to previous data. For Dikes, there's more data for Dayville, and for flows, there tends to be more data for Twickenham with limited monument samples in general. Yeah, that's the main trends we should see here. And then we have a more digestible representation of the same data in this plot. These box plots suggest that there is a strong argument to be made that Monument Mountain is at minimum coeval with Twickenham and intrusively older at minimum. It's interesting to note the most primitive sample, the high magnesium sample, actually presents a younger age, possibly suggesting a flux in mantle material, but these large scale inferences about magma flux require much larger analysis beyond the scope of my study. Here, I've constructed a diagram to compare the extrusive with the intrusive activity. Again, we can see that when compared with the stratigraphy inferred from the type locality at Picture Gorge, the H data is consistent with coeval monument and Twickenham subunits rather than monument following Twickenham. Yeah. So this leads us to a couple of main points of discussion. First of all, the ages of dikes and flows are inconsistent with the stratigraphy established at the type locality. This is evidenced by the expanded intrusive versus extrusive stratigraphy and an ability to confidently geochemically distinguish between flow subunits. This is due to abundant compositional overlap and a small sample size, which complicates confidence in flow member designation when you're using machine learning like principal component analysis or random forest classification. You may have noticed I didn't include any diagrams displaying the flow member designations, just the flow subunits. This is due to the small number of data actually existing for the geochemical compositions of each flow member. So flow members with more data become overinflated when categorizing the data because there's a wider range of acceptable values. As I mentioned a couple times earlier, this is a problem that was first noted when Picture Gorge was established as a formal main phase unit in the 80s. The flow subunits and flow members were first categorized in the 70s based on stratigraphic relationships and hand sample characteristics. Since then, the aerial distribution and eruptive volume of Picture Gorge basalts has almost doubled. And many PGB type lavas have been identified that don't fit neatly into the currently established flow subunits. This effect has become inflated with time and is further complicated by age data that's inconsistent with the stratigraphy for either flow subunits or flow members. So in conclusion, we found that our results are consistent with Emily Cahoon's findings that Picture Gorge basalt is the oldest and longest eruptive member of the Columbia River basalt group, and we expand the stratigraphy at minimum intrusively from 17.27 to 15.61 million years, actually. The eruptive order previously inferred from lava stratigraphy may not be consistent with the age data, but there's a high need for more thorough sampling before we can make any geochemical or spatial inferences about this information. I wanted to conclude really quickly by just saying that, like, while the age data in geochemistry appears very abstractive when considered next to like the bigger picture I started out with, it's important to remember that these age dates and understandings of geochemical evolution allow us to make inferences about things like climatic perturbations or subduction zone hotspot interactions and mantle dynamics. So when these small scale studies are considered in the bigger picture analysis, they actually can hold more weight. Might not be large enough scale to make these connections, but hopefully it supports some studies that do. Yeah, just wanted to give a big shout out to everyone that helped support me throughout the project, and thank y'all for listening.
Thank you very much, Heather. That was absolutely fascinating. And before I get to the questions that came up in the chat, I actually have a couple real world observations from having worked for a couple years since '92 in the Ochuco Mountains and worked with the material sources for engineering projects. And one of the things that I did notice is quite a variation between the Picture Gorge basalts from the basically Big Summit Prairie east, and we north of in the Slide Mountain Pisgah area, there's a lot of what we called basaltic andesite, platy andesite. It was basalt that was starting to develop really good, strong plates, and you got coarser as you move more toward the eastern end of the basalts. So there's a strong variation, and that would be one of those places that, Angela, I'm looking at you too, is that if you guys wanted to do a little more research in the Ochiko Mountains and have some starter points to be looking at, I'd be more than happy to give you a hand. And I know the new geologist on the forest would be too. But that was one of the observations from a real world working standpoint that I found with the geology and the basalts, the picture gorge basalts in the Ochiko Mountains. So, and it looks like they're all kind of falling into that Dayville neighborhood from what I was seeing. So that would be some other flows. So now getting on to, there's a question here starting out. Heather, do your double major focuses sociology and geology overlap? What are you doing with that?
Hopefully they will eventually. They kind of have in like smaller projects or classes. So my earthquake geology class that obviously overlaps a lot more. I mean, volcanics, whenever they happen, not 17 million years ago, but today they do impact people. Landslides, like you can almost take like a people approach to most geologic problems if you just keep it in the back of your head.
Yep, and that's what I found through my career, because engineers could care less whether it was a basaltic andesite, but they wanted to know, is it something that could work for the construction project? And I'm betting that was also something that Carol also dealt with a lot with Hassenberg, with her field of work. One of the things that we definitely want to point out to everybody is folks like Javaria and Angela and Heather and all the other students are benefiting from the vote fund. So if you are feeling the least bit generous, this is an opportunity to support that fund and to support our students who are out there working in the field and gathering new data. That it may be a small project, but it adds to the greater story. John Ogden was curious, what limits sampling? And John, you may need to expand on that for Heather.
Okay. Yeah, the question, there were multiple times where it was mentioned that there were a limited number of samples of the picture gorge basalt, and looking at a map, it doesn't seem like that would be a difficult thing to sample. I'm assuming that that's cost that is limiting the sampling. Is that true, or is it some very specific requirements for the samples?
Yeah, I mean, there are probably a couple things. The first of all is for some of these flow members, they're identified at the type locality, but they haven't really been identified outside of where they were first identified. So being able to identify some of these smaller, not the flow subunits, but like these individual flow members, it's difficult to anticipate where you would expect to find those chemistries. So it's kind of a sample and backtrack process. It could also have to do with accessibility sometimes. We did we were able to map a bunch of extra dikes and stuff because the PhD student I've been working with, Rachel, has a Jeep. We're able to just drive straight up to a lot of it, but it's pretty densely forested and a lot of logging roads out in that area. So even if there's stuff we can see on the map, it's not always accessible.
All right. Another question came in from Kevin W. Is the Plana Lake Obsidian Lava Field south of Central Oregon part of the Columbia River Basalt Group? And are a lot of the lava tubes cave systems east of Bend part of that same group?
Oh, my volcanology professor would kill me. I'm not familiar with Paulina Lake obsidian. Is that like the big obsidian flows by Newberry?
I believe that's what he's referring to.
Yeah, I think it's related, but it's much younger, and I think like more of an adjacent system. It's not really like it's not part of the flood basalt, because the obsidian would be more rhyolite, so like more felsic. But I definitely probably would not be the person to answer that in depth.
So actually I can add to that. Newberry is 400,000 years old, the base with the shield volcano. And it is part of the fault system that runs through that area, but it is not considered part of the Columbia River basalts. They're really baby rocks by comparison, especially now that we're learning about that 15 to 17 million year old age group that's going on. Fabulous talk. And then Wes has a question about the flood basalt provinces in other parts of the world, if they occurred simultaneously or were they widely separated in time. So Javaria, Heather, this could be both of you responding to this.
Yeah, Javaria, if you want to go ahead, have at it.
I think that they're not simultaneously related. They're different ages, and all of them are dispersed through time. And Heather talked about some of them being like the Siberian traps being related to the Permian extinction. So those ones are far more older. And then the Deccan traps have been a lot more younger as well. And so like around that Triassic age. And so they're spread throughout time. And that's one of the things that's very interesting from my understanding of flood basalts, is that there's not a lot of understanding of what triggers something that massive of a size, because these things are huge and we don't really quite fully understand why, like, all of a sudden in time, there's these giant magmatic systems that start to occur. So yeah, to answer your question, there are different ages.
All right. And Leslie was asking about Monument Mountain. Where is it? And Leslie, I assume topographically that that's right outside of the town of Monument. But Heather, have you got a geography link on that one?
I don't really remember exactly where Monument Mountain is. I know it is like right outside of Monument, but I'm not sure which direction. All of our sampling happens to be between Monument and Kimberly, and then south to Burns, about that little triangle. So I'd imagine in this like northern area between Monument and Kimberly, but I'd have to Google Maps it.
We are after 12, and I don't see Gary on the, he's hiding right now. Lots of thank yous, and I have to agree, all three of you were just absolutely amazing today. This is definitely thank you. It has just been such a treat. It has been wonderful today.